So this talk is about higher order fixed point iteration, and in order to talk about this, let's briefly recall what fixed point iteration means. So suppose you have a complete lattice, and for the rest of this talk this will mean also finite, and a monotonic function in this lattice. Then the Knaster-Tarski theorem tells us that this function has a least fixed point in this lattice. And the Kleene fixed point theorem tells us how to compute this by iteration. You start with the least element of the lattice, and then you apply the function to this least element, and then apply it to the value you get, and then apply it again and again and again. And the supremum of the values you get is then the least fixed point. And this gives us a very simple recipe to compute least fixed points by fixed point iteration. The question now is there a better way to do this if the lattice is of a special form, or if you know something about it? And today we are talking about function lattices, so lattices from functions from one lattice to another, and the functions are supposed to be ordered pointwise. And when it's well known that then such a lattice with pointwise ordered functions is complete again. And what we are now going to talk about is local fixed point iteration for higher order function lattices. So for lattices with functions like these, or then from functions from these to other functions, and so on. And in order to give you a feeling for this, let's look at two examples. So the first one is constrained reachability. This means you have graphs labeled by some alpha, beta, sigma. And the question now is, if I have two nodes S and T, is there a word in some language that parameterizes this problem such that I can go from S to T via a path labeled by a word from the language? And for regular languages, this can be done by fixed point over predicates. For example, here is one for the reachability with constraint by sigma star. And if the languages get more complicated, so you have context-free languages, for example, you need to dial up the order. So for context-free languages, this can be done with predicate transformers, that is functions that send a predicate like this to another predicate. And if you want to express reachability constrained by more complicated languages, so say context-sensitive languages, then you need orders even higher. For example, this one here, reachability constrained by a to the n, b to the n, c to the n, can be done with order 2. Another example another motivating example is higher order fixed point logic, which is an extension of the model mu calculus with a simply typed lambda calculus, and this is a program specification language that's extremely expressive, but also quite difficult, so the model checking problem is complex. And what you can express in this are things not expressible in the mu calculus, or also things not expressible in the mu calculus, for example, that all paths in a given structure are finite. Just see you have a fixed point here, and then here you have a predicate transformer. Or you can say that all paths are equally labeled, which means that your structure is bisimilar to a word. So you see this is even more complicated. You have a fixed point with 2 arguments or 2 functions in it. And a lot of other problems can be formulated in this logic. And the semantics are given as in the motivation via higher order function lattices. And model checking here means we have to evaluate fixed points in these lattices. And we have now generalized this and have created a higher order fixed point algebra that was inspired by HFL. And higher order means you need, of course, some types. So suppose we have some base type, which is supposed to type of lattice elements, and if then you then have a collection of types. You can also talk about functions from these collections to the base type, from this collection to the base type again, and these little annotations here called variances tell you whether these functions are supposed to be monotonic or antitonic in this argument, or even more complicated. And what you can prove is that any of these function types forms, or the space of any of these function types forms a complete lattice, again, because, well, functions into a complete lattice. The space of functions into a complete lattice is a complete lattice, again, under sufficient circumstances. So, say you have some lattice and then some function symbols in this lattice, which we are calling basic functions, which are supposed to be built into this lattice. Then you can create expressions in the term algebra, which we call MUHO, excuse me. And you can build them as follows. So each of these built-in functions, of course, is a term in this algebra. We have variables, so a variable is a term in this algebra. And if you have a collection of terms, you can apply them to another term. So we have function application. We have lambda abstraction, so you can talk about functions with some parameters that evaluate to this value here. And then, and this is the important thing, we have least fixed points, so you can have the least fixed point of a term, which is then necessarily a monotone, or describes a monotone function. And at the background, there is a type system going on here to guarantee that this is actually all well typed. So, for example, that you don't have things like f applied to itself, or you apply something to a unary function and you apply to it 2 arguments or something like that. And then this type system also guarantees that we have that these least fixed points here exactly exist. And then this allows us to say, okay, for each well-typed formula, there is a value of it in the lattice, or it has semantics, and then we write it like this. So, let's revisit this constraint reachability problem. Remember that we are interested in this reachability constraint by this language, and we look actually at this structure here. So there's a central element, and then you have 3 loops labeled by A, B, and C of different length. So this is length 1, length n plus 1, and length n plus 2. And the lattice we are looking at here is this one. So we have one lattice element for each node in the graph, and then a bottom and a top. And our base function are the constant 0 function, which always returns the central element. And then we have A, B, and C, which return the A, B, and C predecessor of an element if it exists. We have the function is0, which returns the top element if you put 0 into it, and bottom element else. And note that this is actually not monotonic in its argument. And we have this sort of disjunction, which works like disjunction on the top and the bottom element, and it returns the bottom element otherwise. And we now can formulate this constraint reachability problem as one fixed point here with 3 arguments, which are a lattice element and 2 functions. And we say, okay, test whether the following element is 0, the first argument, and then apply the second argument to it, and then the third argument. And if this is 0, return the top element, and otherwise return the value of the fixed point at arguments where we add an additional A here, an additional B here, and an additional C here. And then you can probably see that this somehow captures this constraint reachability problem. So, the question now, as in this example here, is how to compute the semantics of this formula. And this is clearly possible. If we have a lattice and such a formula or such a term, if it's well typed, this is possible since, the lattice here is finite, so all the base functions are necessarily computable, and the problem becomes decidable just by the naive approach based on the clean iteration and then call by value strategy. So what you do is, for example, if you have a fixed point applied to some argument, you compute the table of the fixed point. So what you do is you enumerate all the possible arguments, so let's say t1, t2, t3, and then you iterate, and at some point you get some results for this, so which tells you the value of the fixed point, say at argument t2 as v2, and then you compute the actual value of psi, say this is v3, and then you just perform table lookup, so you know now the result of this applied to this is v3. But of course this is super wasteful because we compute the whole table, but sorry, that was not intended. We compute the whole table, but we're actually not interested in the value of the fixed point at, say, this argument or this argument. So the idea of our paper is to circumvent this problem and only compute the value of the fixed point at arguments we're actually interested in. So, of course, the hope is that if you want to know the value of the fixed point at argument psi, is to only compute it at psi, but that's not always possible. So, say you have a fixed point that looks like this, so you had one argument, and the value is, say, f of x, or capital X applied to g of x, and now you want to know the value at some argument, and in order to know it, maybe you can compute this, but then you also need to compute this, and then this changes the input. So what you learn is, if you put some value into it, say v1, so in order to know the value of the fixed point at argument v1, you also need to know the value at the value of the fixed point at argument g of v1, and then this possibly continues. So what this means is our approach is to hope for the best. That means we start to build a table like on the previous slide, but just we start with the argument we're actually interested in, and whenever we discover that we need to know the value at a different argument, we just add a new column to the slide, and then we iterate until stability is reached. And stability means that we have not discovered a new argument for a while or for one iteration, and that the value of the fixed point has become stable on all the arguments we have discovered that we need to know the value of. And then the hope is that we don't discover the whole table during this process. And this idea clearly works, so this has been studied for order 1 problems by various authors, and our contribution is to extend this to arbitrary orders in lattices and in the setting of our fixed point algebra. So, and how does this work? We said we need to know the value of an argument to actually compute the value of a fixed point on it. So this suggests to build an algorithm that works top-down, that is, that descends from a formula to its subformulas. And what we also have seen during studying this, that what I said before, if we have an application, we have to compute the full semantics of the operand at this application, because, well, remember the fixed point table before, we said we want to know the value of the fixed point at some argument. Well, then we need to know what the value of the argument is, and there will be some discussion on this on the last slide. And of course, if we have a top-down algorithm that descends from formulas to subformulas, then we need to deal, for example, with free variables and with higher order terms. So what this ends up being is a procedure we have called eval, which has 2 parameters, a term on which we want to know the semantics of, and a number of arguments in case this one is higher order. And the invariant here is that the term applied to these arguments always gives you an object of the base type. And then we have this global variable which we use to deal with the free variables. So if we have if phi has free variables, then we find the semantics of these free variables in this. And then of course we have also the lattice on which we do the evaluation. And what we have proven is that our procedure eval here, that works like this, correctly computes the semantics of this term relative to this variable interpretation, and that's not super straightforward, but also not incredibly difficult. And here's the algorithm. But let's actually not go through all the cases, because that's probably not very interesting. And in fact, let's rather look at an example, and an example you've already seen. So this is this constraint reachability problem from a few slides ago. Remember that this asks whether on the structure that looks like this, is there a path from zero to itself labeled by a word of the form a to the n, b to the n, c to the n, for n greater than 0. And in order to make this a bit more easy, let's say n is 3, so this makes the structure a lot easier to see. So you have like a loop of length 3 here, one of length 4 here, one of length 5 here. And what you also can see is that the functions, or the powers of the base functions for b and c behave rather predictably on this structure. So if I have the ith power of b, and then I have the ith plus 3 plus 1, so like I plus 4th power, then this is actually the same function. And the reason for this is that, well, this gives us the ith b predecessor of an object, and this gives us the ith plus 4th predecessor of this object. And, well, there are two cases. Either an object doesn't have a b predecessor, then this returns false, or the bottom element anyway, or it does, and then you just do an extra loop on the circle. And the same holds for c and for a. And then what you probably know, the least common multiple of these three numbers here is 60. Just for the reference. So how does this work now? Well, we want to evaluate this term on this structure, and this is an application, so we obviously evaluate the semantics of these first. So a of 0 is the a predecessor of 0, so that's this node here, node number 2. And then we evaluate the fixed point here, and evaluating the fixed point means, okay, try to evaluate at this argument tuple first, and hope that we only need to know the value of the fixed point on this argument tuple. And, well, the first iteration, of course, is, in fixed point iterations, always set to the bottom element, so we skip that. And then the zeros iteration, and the first iteration is this one, where we now evaluate this, but is 0 of g of f of x is the bottom element, x is 2, f of x is the b predecessor of 2, and 2 doesn't have a b predecessor, so that's the bottom element, and then g of the bottom element is also the bottom element, and then is 0 returns the bottom element. And this here is the fixed point at an argument tuple which we haven't seen yet, so of the default value is also the bottom element, so we get the bottom element for this. And during this, what we have learned is that in order to know the value of the fixed point on this argument, we need to know the value of the fixed point on this argument tuple as well. So we add this to our table, and now we continue the iteration. That is, we iterate the fixed point on both of the arguments which we've discovered so far, and, well, on this one, this doesn't change because, well, all the values have not changed. And on this one, we get that this evaluates still to bottom, and we discover that we also need to know the value of the fixed point on this argument tuple. And then this goes on, and you can probably imagine that this will go on for a while. And in fact, at some point, what happens is that we have discovered we need to know the value of the fixed point on all these tuples, and this tuple 1, b to the 3, c to the 4. And in the process of evaluating this one, we learn that we need to know the value of the fixed point on the tuple 0, b to the 0, c to the 0. And now something changes because, well, first of all, not here, that this is actually not evaluating to the bottom element but rather to top, because 0 is this element, this is the identity, this is the identity, so is 0 of 0 returns the top element. And then something else is noteworthy here. We discovered during the evaluation of this that we also need to know the value of the fixed point on this tuple of arguments. But note, this tuple is this tuple. So we've already seen this tuple, and of course we don't add another column here if we already have this, but rather say if you need to know the value here, just look here. And we have not discovered a new argument at this step of the algorithm. Well, let's continue for a bit. So what happens now is that we don't discover new arguments, obviously, and at the next iteration, the value of this one here changes to the top element. This part here still evaluates to the bottom element, but then this here evaluates to the top. Just look at the table here, and then so this one evaluates to the top, and then this propagates down, and then at some point this reaches here, and oops. Sorry. At some point, the value of the fixed point at the tuple we were actually interested in is discovered to be the top element. So, what have we learned? Well, we have seen we have 120 columns, 120 rows, and we have 60 columns. And this is obviously quite a table, but let's look at a naive approach where we tabulate all the possible arguments to the fixed point before and then iterate on all of them simultaneously. This actually gives us less rows because we don't have to discover new arguments, we have all of them already in the table, but this gives us a huge table. So consider just all the possibilities for the last parameter g. Well, g is a function that maps objects in this lattice you can't see this lattice, but also maps objects of this node, of this graph to the graph again. And this one here has 9 nodes. So for each of these nodes, you have 9 different possibilities, and then the top and the bottom element. And so this gives you doubly exponentially many possible ways that a function could be of this type could be defined. And then you also have the other function. So this gives us a tremendously large table. And the idea, or what you can see here, is that even though this might give us a table that's a bit higher or has more rows, actually the amount of work to be done here is much smaller than in the naive case. So to sum this up, what we've done is we have extended local fixed point iteration, which is also known as neededness analysis, to higher order functions, actually to functions of an arbitrary order as long as it can be formulated in our higher order fixed point algebra. And we have implemented, or we have seen one example here in this talk where it shows that it's clearly beneficial, and there are several more in the paper where we have argued how this saves a lot of work compared to a naive approach. And we've actually implemented this, so if you want to see this in action, go check it out. And we argue that this might be a candidate for what one should call on-the-fly evaluation for higher order properties, which is not studied well so far. But we are not done. So I said on one of the previous slides that in order to know for this to work on an application, we compute the whole table of an argument, and obviously that can be a lot of work as this argument is of higher order itself. So the question is, can this be avoided? And we are not sure. We have struggled to find a way around this, but we also haven't proved that this is unavoidable. So this is open. And then what's also a question that one could look at is, can one actually guess which arguments one will need beforehand and then speed up the discovery process? So like a human would see that obviously how this would go. So can we teach the computer to do this? And then there are more open questions, but that's it for the day. So thank you for watching this video, and if you're interested or have questions, our Q&A session will be on the very first session on Monday the 21st, 3:15 p.m. Thank you.